Hello, I'm Clemens Altaner from the School of Forestry at the University of Canterbury, and I'm working on durable eucalypts together with the New Zealand Dryland Forest Initiative and ZDFI. The topic of my talk is durable eucalypts for LVL, laminated veneer lumber. And if we look at New Zealand, it has an existing LVL industry based on radiata pine, and there are 3 places where it is made. And LVL is a structural product, so its value is determined by its mechanical properties, and the way an indicator for that is the modulus of elasticity, or the stiffness of the product. And we can see that the products manufactured in New Zealand are between 8 and 13 gigapascal in stiffness. And if we look outside of New Zealand internationally, there are stiffer LVL products available up to close to 17 gigapascals, and that is twice as stiff as the New Zealand LVL products. Now, 17 gigapascals, that is what timber engineers say it's comparable to steel, and they can use such high stiffness engineered wood products to construct really tall wooden buildings. And this is a picture of a study from Sumitomo out of Japan, designing a 350-meter tall all wooden skyscraper. And it cannot be made from lower grade LVL, but they need high stiffness engineered wood products to achieve that. Okay, so why can other people make this high stiffness LVL and we in New Zealand don't produce it? And it has to do with the wood which we have available, which we use to make the LVL out. We make it out of radiata pine, and if you look at solid timber, New Zealand grown radiata pine, in average it has a stiffness of 8 gigapascals, but there's some wood which is stiffer, and there's also wood which is less stiff. Now, if you look on the LVL products, the average stiffness is higher, let's say 10 gigapascals. And how can that be? It is achieved by creaming up the stiffest logs and the stiffest parts of the logs and converting it into veneers and using it for LVL production. Now, the data comes from a study from Doug Gaunt at Zion. And in this study, they actually looked at using Eucalyptus nitens for LVL production. And they have shown that you can make a really nice LVL product out of Eucalyptus nitens with an average stiffness of at least 14 gigapascals. So now we know how it's technically possible to achieve that. It's by using other wood. And while we have a resource of a smallish resource of non-durable eucalypts like Eucalyptus nitens, fastigata, and regnans, I particularly work with NZDFI on ground durable species, bosistoana, quadrangulata, and globodia. And while they have not really been chosen for their mechanical performance, but for their ground durability, it happens to be that they also produce very stiff and strong wood, more than 20 gigapascal in stiffness, and therefore they are really good starting place, a good material to start making LVL out of it. So while we now have a technical solution to it, to the problem of how to make stiff LVL, we asked the question, is it also an economically viable proposition? Is there a business case for them? And the way we approach this is looking at all the variation which we have in trees, in terms of shape, in terms of stiffness, and what we know about Eucalyptus bosistoana, and then see how these individual factors of shape, of stiffness, of shrinkage affect the value of a tree when it is converted into into veneers for LVL protection. We know the value of the veneers, and we also know the properties of the trees. So we can figure out what's the sensitivity of the value of different factors. So we looked at volumetric shrinkage, stiffness, geometry of the logs, the amount of usable veneer which we can get out of the trees, and then a lot of different ways how we can convert the logs into veneers, different peeling technology. And to figure out the sensitivity, we compared a bad case with a good case. And while there are some variables which don't affect the value of the trees at all, we are not really caring about it. The single most important one is the amount of usable veneer which we can get out of the logs. So what do I mean with usable veneer yields? I mean what is visualized here. So we actually have taken some of the durable eucalypts to a LVL plant, peeled them into veneers, and from some logs we get really nice veneers out of, and also in good yields. But there are some logs in there where we hardly get any veneer out, and the veneer we get out is full of these cracks at the end. And these cracks are a direct consequence of growth stresses in the trees. And growth stresses are really the single most important factor preventing eucalypts from being used in solid wood products. And, this is affecting hugely the yield for the eucalypts. Now, we also know that there's a solution to that, because growth stresses are variable, so there are good logs in there with low growth stresses. We know that they are under genetic control, and we have a means of measuring them really quickly in a breeding program. So we can reduce the growth stresses, we can increase the yield of usable veneer in the peeling process with planting better genetic stock. And we have assessed species of the Dryland Forest Initiative for low growth stress, and these plants will now be available for planting. I also want to mention that this problem of growth stresses and end splitting in the veneers is not unique for the durable eucalypts. It also applies for Eucalyptus vastigata and nitens, the non-durable species of which we have a small forest estate here in New Zealand, but they have not been screened for growth stresses yet. Okay, now we know the problem, but we also know the value of the trees, and we also know the growing costs of Eucalyptus bosistoana trees, depending on the growth rate on the site and depending on planting subsidies. The growing costs for Eucalyptus bosistoana tree to get it to 30 centimeters dBH is between $20 and $56 per tree, and that already includes an internal rate of return of 8% to the forest grower. So if we can sell it at that price, the forest grower makes a profit. Now the value of those trees, depending on the wood properties, depending on the technology we use for peeling, is exceeding that. So even in the worst case scenarios, the value of the trees is exceeding the growing costs. So this margin, which is between there, needs to cover not only the profit for the manufacturers, but it also needs to cover harvesting costs and transport costs and production costs. So now it's up to the LVL manufacturer to see if this margin is actually big enough for them to also make a profit. So there is a business case for planting those trees out. The trees are becoming now available, and there's lots of research going on in the space of durable eucalypts with postgraduate students here at the School of Forestry, a larger team of researchers in the NZDFI, and a lot of support from the government and the industry to undertake this work. Thanks for watching, and I hope to see you soon in person.